Welcome to Life with David. I'm David, and today we're continuing our bare metal adventure with the RP2040. In the past, my demonstrations have been limited to using only one of the two cores of the RP2040. But last time, I installed Doom on the Pico and got to see what two-core operations could accomplish. If I want to incorporate a graphics display in the future for the Pico, I'm going to have to use a second core. So why don't you join me as we explore bare metal RP2040 two-core operations? As you probably know, the RP2040 has two ARM Cortex-M0 Plus cores. The default configuration is for Core 0 to execute code while Core 1 sleeps. Core 1 will remain in sleep mode until it is woken by a user code. Coordination between Core 0 and 1 is handled by the SIO, or Single Cycle Input-Output block. This block connects the I/O ports of both cores and is not attached to the main system bus. The CPUID FIFO and Spinlock registers in particular are essential for two-core operation. Let's go through the function of each register. When both cores are churning through code at the same time, you sometimes need to know which one is doing what. This is where CPUID comes in. Reading the CPUID register will return a 0 for Core 0 and a 1 for Core 1. Communications between the cores are handled by the FIFO, or first in, first out registers. These are like one-way mailboxes. That is, Core 0 can send a message to Core 1 through one FIFO, and Core 1 can send a message to Core 0 through the other FIFO. Flow control is facilitated by the FIFO status register. These registers have a unique addressing scheme. Even though there are two separate FIFOs, they have the same addresses for the transmit, receive, and status registers. Each core can only access the registers and flags associated with it. That is, Core 0 can only access the transmit to Core 1, receive from Core 1, as well as the associated flow control flags. The transmit and receive registers are located at D0000, 0054, and 58 hex respectively. We'll use the FIFO shortly to wake up Core 1. There are 32 Spinlocks which can be used to grant mutually exclusive access to shared resources. They're used to prevent racing conditions. They're kind of like an occupied sign on an airline bathroom. But unlike the occupied sign, Spinlocks have no hardware interlock to prevent access. They're just flags that are shared between the cores. They can be used for anything the programmer wants. In practice, one core will claim a particular Spinlock flag if they want exclusive access to a given resource. If the other core wants the same resource, it will check that Spinlock, but if it's already been claimed, it will sit and spin on that register until the first core releases it. Then the second register will claim the Spinlock and access to the resource. The first program I'd like to demonstrate wakes up Core 1 and then uses the CPUID to blink two different LEDs, one for Core 0 and one for Core 1. I'll start by modifying the program from Bare Metal Adventures Chapter 8. As a reminder, since this program does not use the C++ SDK, it includes code to initialize the system clock, set the GPIO, configure the UART, copy the main program into the static RAM, and finally transfer execution to the main program. For more information, please see my Bare Metal Adventures Chapters 6, 7, and 8. I'll leave links in the description below. In the main program, I'll first configure GPIO 4 and 5 as outputs. Next, we have to initialize Core 1. As mentioned earlier, Core 1 puts itself to sleep just after entering the boot ROM on startup at about address 174 hex. Per section 2.8.2 of the RP2040 datasheet, Core 0 uses the FIFO to send a wake-up message to Core 1. This message consists of 6 words: 0, 0, 1, the address of the vector table for Core 1, the address of the initial stack pointer for Core 1, and finally the address of the program entry point for Core 1. The reason for the 001 code at the beginning is to prevent spurious events from inadvertently waking Core 1. To accomplish that, I'll write a routine to transmit one word from core 0 to core 1. After core 1 receives the word, it will echo it back to core 0 for a validity check. So I'll need another routine to read a word from core 1 to core 0. Finally, to ensure no garbage data is received from core 1 during the echo, I'll write a routine to drain the FIFO prior to use. Since it's the first routine called, let's start with draining the received FIFO. Each FIFO can hold 8 32-bit words. Since core 1 is asleep, artifacts are possible in the received FIFO from core 1, so section 2.8.2 requires that it be drained before reading. The FIFO status register, located at D00000050 hex, contains flags that tell us whether the transmit FIFO is full or the receive FIFO is empty. To drain the FIFO, I'll first load the SIO base of D000000 hex. Then I read the FIFO receive register at an offset of 58 hex. Discard that data and read the FIFO status register at an offset of 50 hex. Isolate the receive FIFO not empty bit, which is bit 0. If that bit is not 0, then there's still data in the FIFO, so branch back and read and discard another word. Keep checking until the receive FIFO is empty and then return. To transmit a word that is located in register 0, read the status register and isolate bit 1, the transmit FIFO not full flag. If that flag is not set, then the transmit FIFO is full, so spin on that flag and wait until there's room in the FIFO. When there's room, store the word in register 0 to the transmit FIFO register at an offset of 54 hex. At this point, we need to wake up the other core. The instruction SEV, or send event, sends a wake-up signal to all cores. Any core which is asleep will wake up starting at the location where it went to sleep. In this case, core 1 went to sleep near the bottom of the boot ROM at approximately address 174. After core 1 wakes up, it reads the FIFO. If the correct code was sent, core 1 echoes the code back to core 0 through the FIFO. If not, core 1 goes back to sleep. To read the FIFO, first read the status register and isolate bit 0, the receive FIFO not empty flag. If the flag was not set, then the receive FIFO register is empty. We can wait for incoming data two ways. We could continue to spin on the status event, waiting for bit 0 to set. However, since core 1 sends an event whenever it sends a word to core 0, we can also just wait for an event. That's what we'll do here. After the event, return and check the status register again. If the flag is set, then get the word from the FIFO receive register and return. Okay, let's use these routines to wake up core 1. As a reminder, we're going to send 0, 0, 1, the address of the core 1 vector table, the address of the core 1 stack pointer, and the address of the core 1 entry point. I'll start by draining the FIFO, then load a 0 as the first word to send. Send the word and then read it back. If the readback is correct, in this case 0, we'll proceed to the next word. Otherwise, we'll start over. I'll do the same thing for the second 0 and the 1. Next, I'll send the starting address for the core 1 vector table. Since this is just a short demo, I'll use the same vector table as core 0. For more sophisticated uses, I would create a separate vector table that would provide core-specific interrupt vectors. This section of code follows the same format as the previous ones, where we send the word and verify the echo. I'll do the same thing for the stack pointer. Here we must choose a different stack for core 1 than we have for core 0. If they're the same, they'll walk all over each other and will crash. I've chosen to start core 1 stack at 2004 1000 hex. Finally, Core 1 needs to know where it will start executing code. I'll use the ADR instruction to grab the address for the label entry and store it in R4. We'll have to add 1 to the entry address to convert it to thumb mode. Then I'll send it to Core 1 like all the other instructions. Okay, now that Core 1 is awake, we'll put together a program that will blink 2 different LEDs based on the core number. In this routine, Core 0 will blink GPIO4 and Core 1 will blink GPIO5. I'll start by labeling the routine entry, which is where we told Core 1 to start earlier. Then I'll output enable GPIO4 and 5. Within another loop, I'll load in the CPUID of the CPO that's executing the code. This will either be a 0 for Core 0 or a 1 for Core 1. I'll set up to blink GPIO4 by moving the atomic set and clear bit to bit 4. Then I'll shift the atomic bit over by the CPUID value. That means that if Core 0 is executing the code, the atomic bit will shift over by 0 bits and GPIO4 will blink. If Core 1 is executing the code, the atomic bit will be shifted left by 1 bit and GPIO5 will blink. Then the atomic set and clear registers will be used to turn the appropriate GPIO outputs on and off. Delays will be added so we can see the blinking. The entry routine is entered differently by the 2 cores. Core 0 enters the program as it completes initializing Core 1. I added a delay in order to stagger the blinking. Core 1 enters the routine without a delay after it wakes up. Let's try it out. Put these files in the project folder. Then, in the Visual Studio command prompt, navigate to that folder. Type make clean and then make full. After connecting the Pico using the boot select button, copy over the UF2 file. You can see that both GPIO4 and 5 are blinking, demonstrating that both cores are running. Now with both cores running, there can be a traffic jam when both cores try to access the same resource at the same time. As mentioned before, there are 32 Spinlock registers that programmers can use as traffic cops for these resources. This program utilizes a Spinlock so each core can alternately blink short or long blinks. The result will be the familiar Morse code SOS. Let's get into the details. I'll keep the initialization of GPIO4 and 5 even though we won't use them this time. The initialization of Core 1 is the same, as well as the FIFO receive, FIFO send, and FIFO drain routines. After waking Core 1, Core 0 starts the entry C0 routine. The first thing Core 0 does is to query Spinlock 0. In this program, Spinlock 0 is used as the traffic cop for the onboard LED. This register is located at an offset of 0 hex from the Spinlock base of D0000100 hex. If a Spinlock is read and the result is not 0, then the core that read the Spinlock has successfully claimed the Spinlock. Subsequent reads of this Spinlock will result in a value of 0, meaning that the Spinlock is locked and the other core has to wait until the Spinlock is released. A Spinlock is released when any value is written to it. If Core 0 claimed the Spinlock, then 3 will be loaded into register 0. LED count will be called to blink the onboard LED 3 short blinks. After a long delay to separate the blinking group, Core 0 will write any value to Spinlock 0, releasing the onboard LED for another user. I needed to insert a no-op here so there's enough of a delay for the other core to jump in and claim Spinlock 0 for itself. If there isn't enough of a delay, Core 0 will immediately claim Spinlock 0 again, and Core 1 will never have a chance. Then Core 0 will jump back to the beginning and do it again. Meanwhile, Core 1 is executing routine entry C1. This is similar to the entry C0, except it first claims Spinlock 0 and then blinks the onboard LED 3 long blinks. After a long delay, Core 1 releases Spinlock 0. But instead of immediately returning to the beginning, Core 1 will spin on Spinlock 0 again. During this time, Core 0 should be executing entry C0 and blinking the onboard LED 3 short blinks. After Core 0 has released Spinlock 0, Core 1 will claim Spinlock 0 again and execute a very long delay to separate the SOS messages before releasing Spinlock 0 and returning to the beginning. Let's try it out. We can see that Core 1 grabs the Spinlock first with 3 long blinks, and then Core 0 takes its turn. After Core 1's very long delay, the familiar SOS pattern emerges. Thanks for joining me today. This time we explored using the 2 cores of the RP2040 at once. We got both cores to use the same code, but blink different LEDs. Then we got each core to run a separate routine, but blink the same LED. 2-core operation will help me with future RP2040 projects, so stay tuned. If you like this video, or you think someone else might, please give it a thumbs up. If not, give it a thumbs down. The more likes this video has, the more YouTube will recommend it to others. Also, please leave a comment or suggestion for things to do. I hope to do more of these videos, so please subscribe and click on the bell for notifications of new videos. Let's get together next time for another day in Life with David. See you soon. And there it comes.
Oh, yeah, you gotta put your glasses back on.
Yep. That was totally awesome.